funny as I do. But when I went, this is, you know, I do this similar times each year. When I went to go back and edit the slide, the only thing I had to edit was from 414. I had to just change this number right here from a 4 to a 3. And then I'm set for this semester from last semester. Is that not awesome or what?
414, so
Yeah.
that's all the way on the...
Yeah, it's not 414.
Okay.
That's what I had to edit. So this one's correct. Yeah, this one's correct. So 314 is the ICN room. So we should be set. So today, like I said, probably will not be here the whole class period. Hope you're not disappointed. So fractional precipitation. Fractional precipitation. They are kind of fun. They piggyback on this idea of regular precipitation, which, like we talked about, basically you calculate a Q, a QSP, and compare it to your K or KSP. And if it's larger, then a precipitate will form. That's it. Bottom line. But in this case, we are actually going to have a possibility of 2 different insoluble salts precipitate out. So it just kind of helps just to kind of show you. So, okay, the figure's coming up in a minute. So you're going to drip basically, or I guess you wouldn't have to drip, but basically you're going to add a certain amount of cation or anion that will form a potentially a solid precipitate with the other anion/cation. Okay. So, and depending upon the solubility products or just the general solubility, they're going to kind of fall out at different times based upon the concentration of the thing that they can both precipitate out with. So, for instance, the thing that that chromate and bromide can potentially precipitate out with is actually silver. Okay. So we're going to drip silver nitrate. Nitrate is the spectator ion. We're going to drip it in here, and we're going to see which one's going to precipitate out first. We're going to work problems quantitatively, but I'm just going to show you that this is the situation. So, in other words, I went ahead and let the cat out of the bag, that if you start out with the same molar concentrations of these 2 potentially anions, insoluble salt, that form insoluble salts with silver, it's going to be the bromide that precipitates out first. Now, you couldn't know that until we're going to work some problems to know that. So notice that your bromide ion is almost entirely precipitated out here. If we drip in a molar concentration of the silver, I guess if we drip in a certain amount of silver nitrate, notice that almost all of your bromide is precipitated out. If you started with 0.010 molar, right now with this precipitate here, we have 5 times 10 to the minus 8th molar. I'd say that's significantly not much left in from what you started with. Notice the molar concentration of chromate ion did not budge. That's the beauty of fractional precipitation. If you have a nice separation between the insolubilities of these 2 salts, you can get one to come out and the other one will stay in. Okay, so that's fractional precipitations. So we're going to work, I think, just one problem. Okay, so in this case, you know, I kind of tend to draw these pictures. In this case, we have, I just need to throw that one away. We have down here the molar concentration of cadmium-2 is equal to the molar concentration of nickel-2 is equal to 0.020 molar. Oh, cadmium, no, that's one of the, this isn't cadmium-2, it's just simply cadmium. Ah, oh, got me. Chem 1 thing. Remember, zinc, cadmium, and silver, they're transition metals, but they form a +2, +2, and +1, respectively. So we don't use Roman numerals with cadmium. Anyway, so we're going to drip in sulfide. It doesn't say what the spectator cation is. This is like how I think of it. We're going to drip in S2 minus. Okay? And we're going to have to see which one is going to precipitate first. Is it going to be your cadmium sulfide or your nickel 2 sulfide? Okay, that's it. Which one's going to precipitate first? And then oftentimes there's a follow-up question, and this particular follow-up question is, when the second compound begins precipitating, what is the concentration of the first one that remains running around in the solution? So we're going to answer both of those. So when you're faced with this in homework and or on a test, you can't go wrong, or should I put it another way, you really should go ahead and write the KSP expressions. I would actually write the equilibrium of the insoluble salts. I don't know why sometimes we get in a hurry. We just like, and that's coming up on the next slide. But, so the compound with the lower solubility will precipitate out first. That'll be the answer to the first one. Okay. So here we go. This is what I started to say. You really should put these both up when you're working this sort of problem. What is this? This is the equilibrium constant of dissolving one of the two insoluble salts, along with the KSP expression. And as I was getting ready for lecture, I thought, you guys are with me on this, that this number over here, this 3.6 times 10 to the 29th, you get that from a table, and or it will be given to you. That's the solubility product constant. So that one is for cadmium sulfide, and then we do the other one for nickel 2 sulfide. The nickel 2 sulfide solid is in equilibrium with the cation, nickel plus 2, and the sulfide ion. And again, that 3.0 times 10 to the minus 21st, that you get from a table. That you have to be, in this sort of problem, to be given to you. But we did work problems where you could come up with it, calculate the KSP. All right. So what we're interested in is basically the point at which basically your Q is larger than or equal to or exceeds your K. Okay? So in order to kind of find that sweet point, that threshold, we can actually take the KSP expressions you wrote a minute ago and we can solve for the sulfide ion concentration. It looks like this. Okay, there's your KSP expression, and you guys don't have this, but I just brought it in to remind you. If you rearrange that, solving for the sulfide ion, it looks like this. The sulfide ion is equal to the KSP value, 3.6 times 10 to the minus 29th, divided by the molar concentration of the cadmium ion. Just rearranging the KSP expression. That third amount there, given in that triple equality, I don't like triple equalities. This right here is substituting in. Of course, that's the KSP in the numerator, and the denominator. That, my friends, is this. That's the molar concentration of your cadmium ion. So for this particular insoluble salt, the sulfide ion, the molar concentration of sulfide ion kind of threshold, the sweet point is 1.8 times 10 to the minus 27th moles per liter. That's the tipping point. Anything more than that and a precipitate will form. Anything less than that and a precipitate will not form. It's the tipping point. That's the way I think of it. So if we do a similar thing for the nickel 2 sulfide, rearranging the KSP expression to solve for the sulfide ion, okay, we get the sulfide ion is equal to KSP divided by the molar concentration of the nickel 2. Substituting in, that's equal to that KSP 3.0 times 10 to the minus 21st divided by the molar concentration of the nickel 2, which was 0.020 moles per liter. The tipping point then, the threshold of the sulfide ion at which the nickel 2 sulfide will or will not precipitate, is 1.7 times 10 to the minus 19th. Now, I think I've said this before. There are some things where I would have to compare these two quantities a few times, and I guess it wouldn't take me too long to see that, you see that that one is significantly smaller. What does smaller mean? Smaller means it's got a smaller threshold. It means you don't have to drip in as much sulfide in order to get it precipitate out. The answer to your first question is that actually the cadmium sulfide will begin precipitating first. That's it. I hope that makes sense. And like some other chemistry problems, there could be another way that you could think through this. So you might have been thinking this way back when we started this problem, say, Mrs. Snipes, since they both break up to give two particles, since both salts are basically A1, B1, one cation, one anion, okay, they take the same form, we can actually compare their KSPs directly, and you are right, okay? But you can't count on that. I gave you one on the test, probably could not count on that. Okay, so the follow-up question for this particular one says, so when your second compound begins precipitating, so when your nickel 2 sulfide begins precipitating, because your cadmium sulfide is going to come out first. When your nickel 2 sulfide begins precipitating, what will the molar concentration of your cadmium be in the solution? So to do this, we look at our second threshold a few slides ago. We came up with that larger amount for the sulfide concentration of the nickel 2 sulfide. Okay, so we had this number here. That tipping point for the nickel 2 sulfide to begin precipitating, we said the sulfide ion concentration had to be this, 1.5 times 10 to the minus 19th moles per liter. Well, if we use that as the molar concentration of the sulfide ion, we can go back to the KSP expression for the cadmium and substitute that in for the sulfide ion. It looks like this. So this is the KSP expression for the thing that precipitates first. Basically, what we're going to do is solve this KSP expression for the molar concentration of cadmium. Of course, that is equal to KSP divided by the sulfide ion concentration. And we said at the point when nickel 2 sulfide begins precipitating, we know what that molar concentration of sulfide ion is. It's 1.5 times 10 to the minus 19th. So now if we take the KSP 3.6 times 10 to the minus 29th divided by that tipping point for the sulfide ion, when the nickel 2 sulfide begins precipitating, 1.5 times 10 to the minus 19th, we get 2.4 times 10 to the minus 10th moles per liter. So that's what the cadmium ion will be. See, I told you we'd get done early. So let's take a look at these. These will be due on Wednesday. So on Wednesday, we're going to go ahead and start Unit 4. I don't think I relabeled this. Didn't relabel it, but it's here. I know you're here. There you are. It's a weird one. It kind of looks, well, I got my burette thing going on there. That's why it looks weird. So these works pretty good for to me, I think of that's a way to dispense a small amount of, in this case, if you read the problem a few times, basically you're admitting 0.1 molar of sodium chloride, 0.05 molar sodium sulfate, 0.001 molar sodium hydroxide, 0.5 molar sodium carbonate. So the thing of interest then is you have two cations. You have the barium and calcium. And there's those molarities. So this is what the problem says. And it says that basically running 4 different experiments, dripping in those above, how are we doing for separating, in the first case, separating, barium chloride from calcium chloride. Can we separate barium sulfate from calcium sulfate, get it, barium hydroxide from calcium hydroxide, barium carbonate from things like BR, but barium carbonate for calcium carbonate. So my idea kind of looks like this. Again, there might be more than one way to skin this cat. But if I kind of make a column like this, so it kind of goes back to this problem. Usually you can't look at KSPs and know their solubilities directly unless the same number of particles are being formed by both salts of interest. And that is the case here. So actually we can look at KSPs, just use KSPs to get a sense for what the solubility is. So this will involve, to me, looking up these little check marks. Should be, if they are an insoluble salt, these little check marks will be great at, you'll look these up in tables. These check marks you'll look up in a table. What is the KSP for barium chloride? What is the KSP for calcium chloride? Okay. Let's see. Oops, I guess I didn't. So my little hint back up here then is, in red. If they're both soluble, then it's not a good technique for separating your barium and your calcium. Okay. If they're both soluble. If they both precipitate out at about the same KSP, that's not good either. So basically what you're looking for is where you have KSPs that vary by 10 to the minus 4th, 5th, okay? And then one will come out first and then the other one will follow. That's good. The next one looks like this. Again with the picture. So you have the 2 cations, and I'm not even reading the problem, just look at the pictures. Looks like we're going to drip in the iodide cation, and we're going to see if lead 2 iodide or silver iodide is going to precipitate out. This is very similar, like I said, to the last problem we did with the nickel 2 and the cadmium. So if you're going to kind of play it similar to what we did the problem in class, then you're basically going to kind of do exactly what we did in class, come up with the iodide threshold for the lead 2 iodide and the silver iodide to precipitate from their KSP expressions. Okay, and then make a judgment call which one is lower, which one's lower threshold, that one will precipitate out first. And number 2 is, again, I think if you look at the example we did in class, you should be fine. I guess it's for C. And in this one, we have 2 polyatomic anions in there, and we are going to see if they are going to precipitate out with lead 2. And I went ahead and I really would strongly urge you on a test. Sometimes I'll even pull it out of you on a test. So we're talking about insoluble salts. Can you write the KSP expression or the equilibrium for the insoluble salt? This is what I'm after. You're just a hop, jump, and a skip away from writing the KSP expression then. Okay, and you guys have had homework to try to do that. We'll work it similarly to the previous problem. And last but not least, we have the chloride and iodide. See if it's going to precipitate out with silver. And I think my hints were, I don't think I had any hints. I'm kind of like, see previous problem. So they're all very similar. So these will be due on Wednesday. Okay?
So the first problem, are we not doing
any math really, it's more just
Right.
observing?
Yep,
Okay,
yep, the first one, there's no, just looking it up.
okay.
And to me, and I haven't looked at this closely for like a year or so, but I think sometimes, like, some of these, like calcium chloride, I think it's behaves kind of like sodium chloride. I think it's pretty soluble, so I don't think you're gonna find a KSP value for calcium
And you
chloride.
said you can only
It's not.
compare.
Okay, go ahead, no.
I was gonna say, can you only compare the KSPs when it has the same number of particles? You said?
Right.
Okay.
Because what you're really after is solubility, molar solubility. And KSPs are an indication, but remember, like if you had, you know, BA CL2, you know, in that case you have 3 particles, and you couldn't compare it with NaCl, because that's only 2 particles you have. Yep. Okay? So I started to say, if something's insoluble, which one we can and to me, the fact that it says which one of the following can be used to separate, only one of them is going to fit the bill, if I read the problem right. And if something's soluble, I don't think it's a good one, I don't think. Although if it's soluble, you could remove the other one and leave the other one behind. It's funny, I was thinking about this. You get the sludge down here and you have the other one. Well, it could be that you want the sludge, or it could be that you want it purified. You want the liquid purified. So either one of these fractional precipitation is kind of nice. So go and ponder.